So I thought it'd be fun to do another bonus question for solving for a gaseous reaction, just because it has been a certain amount of time, by which I mean like probably about 3 or 4 weeks since we've done a lot of stoichiometric problems. So it would be a good idea to practice. We just did a question where we ended up with calculating our volume of gas last, okay, because we were given information about the reactant in terms of mass in grams, etc. So this question is basically asking us to do the opposite, where we have the information about the gas first, the product that's collected, and we've got to work back to work out what mass of reactant there was. Okay, so it's quite a nice little mental workout to do it both ways. So again, we're just using the PV equals nRT, the ideal gas equation. So we're starting with our dinitrogen gas. We've not got a balanced chemical equation, so we're going to have to do that. So the decomposition of sodium azide, the azide ion is N3, like 3 nitrogens bonded together with a 1- charge. So if you're wondering how the heck that balances, that's how that balances. So sodium +1 and the azide ion 1- actually does balance out. So it decompositionizes it decomposes into solid sodium and gaseous dinitrogen. Okay, so let's see, 3 versus 2 is not going to mix, so let's look at the lowest common multiple. 2 times 3 is 6, so let's make that we have 6 nitrogens on each side and fix the sodium last. That'll do, right? Okay, so now we have a balanced chemical equation. We're asked to relate moles of dinitrogen gas to moles of sodium azide. So for every 2 moles of sodium azide that react, they will form 3 moles of dinitrogen gas. So that is our mole ratio in terms of an equivalency. So we've got the volume, we've got the temperature. Oh, good lord. Temperature is in degrees Celsius. That will not do. We have to add 273.15 to get our temperature in Kelvin. So that is going to be 277.287.15. Okay. Are we good? Yeah, we're good. So we're going to rearrange PVRT to get the N, which is our number of moles of dinitrogen gas. So N equals PV over RT. So pressure is 1 atmosphere, volume is 56 liters, R is 0.08206 liter atmospheres per mole per Kelvin, T is 287.15 Kelvin. So we should just end up of units of nils, correct? Yes. So atmospheres cancels, liters cancels. 1 over 1 over moles is just moles. So we should get our number of moles of carbon dioxide, which should be, I have to calculate this, aren't I? 56 divided by 0.08206 times 287.15 gives me 2.37655 moles of CO2. Okay, so then we're just going to use our mole ratio to convert, okay? So 2.36, whatever that is, moles of carbon dioxide, the mole ratio. I'm going to put my moles of carbon dioxide on the bottom and my moles of, why am I saying carbon dioxide? It's not carbon dioxide at all, is it? It's nitrogen gas. Oh my gosh. Sometimes I just wonder. I really do wonder. Right, well, I can fix this bit. I can't fix that bit because I already pressed return. Moles of NaN3 on the top. We haven't used any molar masses or anything, so it doesn't matter because gas identity doesn't matter, right? That is one of the principles of the ideal gas law. Okay, so 3 moles of dinitrogen gas to every 2 moles of sodium azide. Now it matters. Okay, so I've got my moles of sodium azide, and what I can do is I just go straight ahead and use my molar mass of sodium azide to convert moles to mass in grams. So sodium is 23.99, nitrogen is 14.01-ish times 2. So the molar mass of sodium azide should be, hang on, 14.01 times 3 plus 22.99 is not 2.99. I think I need to change the batteries in my calculator, or I'm just pressing the buttons too fast. is 65.02 grams per mole. So 65.02 grams for every 1 mole of sodium azide. So that should give me my mass in grams of sodium azide. What's it going to be? 2.37655 times 2 divided by 3 times 65.02. Bam, bam, bam. Gives me about 103 grams of sodium azide. Ain't that nice? So you could always verify that your units are cancelling, like so. You end up with mass in grams. All right, so most of that's just a stoichiometry problem. The only difference is you have a gas as one of the reactants or the products, so you've got to use the ideal gas law to get the number of moles of that gas.